Nonmetals are insulators or semiconductors, and their oxides are acidic. They are highly electronegative, meaning they will gain electrons instead of losing them. Nonmetals form ionic bonds with metals by gaining electrons or covalent bonds with other nonmetals. Hydrogen, a nonmetal, is a colorless, odorless, highly flammable gas. It is the lightest and most abundant element in the universe. Hydrogen is the main energy source for our sun. Two hydrogen atoms are fused together, forming helium and releasing light and heat energy. Carbon is a solid with several different physical forms, called allotropes. It can appear as a dark, brittle material called graphite, or as diamond, the hardest natural substance known. Nitrogen, as a gas, is colorless, odorless, tasteless, and inert. Nitrogen makes up 78% of Earth's atmosphere and is an important component of many proteins and fertilizers. Oxygen is a colorless, odorless gas, abundant on Earth, and necessary for the support of many forms of life. Oxygen is formed primarily as a result of plant photosynthesis. Phosphorus has three main solid allotropes: white, red, and black. Because it is highly reactive, it is never found as a free element in nature. Pure white phosphorus ignites spontaneously in air. The red allotrope is used in matches. Sulfur, once known as brimstone, is a yellow crystalline solid. It was a main ingredient for medieval alchemists. Selenium is a gray nonmetal that conducts electricity better when exposed to light. It is also a trace element that helps the thyroid gland function, but many of its compounds are extremely toxic. There are far fewer nonmetals than metals on the periodic table, but nonmetals make up most of the Earth and its organisms. Because of their high electronegativity, the gaseous nonmetals exist naturally in a diatomic state. Hydrogen, nitrogen, and oxygen form molecules made up of two atoms bonded together. This molecule is much more stable than a single atom. Phosphorus, sulfur, and other nonmetals also form polyatomic molecules. Phosphorus makes pyramids of 4 atoms each, and sulfur exists naturally as a ring of 8 atoms. This tendency to form polyatomic molecules can be explained by taking a closer look at the periodic table. The elements are listed in order of their atomic number, which represents the number of protons in an element's nucleus. In its normal or ground state, this nucleus is surrounded by an equal number of electrons. As the atomic number increases, generally so do the size and mass of the atom. As you read the periodic table from top to bottom, each horizontal line is called a period. This represents the number of electron shells the element's atoms normally have. For example, an atom of nitrogen has 2 electron shells, so it lies in period 2. And an atom of selenium in period 4 has 4 electron shells. Each of these shells can contain up to 8 valence electrons. As you read the table from left to right, the vertical lines of elements are called groups. Elements in one group have the same number of valence electrons in their outermost electron shells. These are called valence electrons, and they usually dictate how elements interact. The nonmetals are to the far right of the periodic table. Not including hydrogen, they span groups 14 through 16 and have anywhere between 4 and 6 valence electrons. Hydrogen is in group 1 above the alkali metals, but it behaves as a nonmetal in most circumstances. It has 1 valence electron, but its valence shell is complete with 2. The type of bond a nonmetal forms depends on its own valence electrons and on the type of element with which it is bonding. Generally, nonmetals will share electrons with other nonmetals in a covalent bond. and take electrons from more electropositive metals in an ionic bond. Carbon, with 4 valence electrons, has the most flexible bonding properties. It usually does not form ionic bonds, but it is able to form rings or long chains by bonding with itself. This versatility accounts for the wide range in appearance of carbon's allotropes. Oxygen, with 6 valence electrons, will take electrons from metals to bond ionically. In fact, when any element is oxidized, it gives up electrons. Nonmetals may be a minority on the periodic table, but they make up the majority of the world around us.
Element number 1 on the periodic table is hydrogen. The atomic symbol for hydrogen is H. Hydrogen is a very light, odorless, and colorless gas that is extremely flammable. Hydrogen is the simplest element and the most abundant in the universe. Hydrogen gets its name from the Greek words hydor and genomai, which means to bring forth water, because when hydrogen is burned, it produces water. Hydrogen is classified as a nonmetal. It lies in the periodic table's first row, period 1. Each hydrogen atom consists of 1 electron that surrounds a compact nucleus, which contains almost all of the atom's mass. In the most common form of hydrogen, its nucleus has only 1 positively charged proton. Unlike all other elements, hydrogen has no uncharged neutrons in its nucleus. 1 negatively charged electron balances hydrogen's 1 proton. Hydrogen's electron is found in the single orbital shell that surrounds the nucleus, the sphere-shaped 1s shell. This single valence electron determines hydrogen's unique chemical behavior and makes hydrogen highly reactive. In this experiment, a partly filled plastic bottle contains hydrogen above water. When the water is emptied from the bottle, air, which contains 20% oxygen, rushes in to take its place. When a lit taper is placed near the bottle's opening, the hydrogen and oxygen ignite to project the plastic bottle through the air like a rocket. The products of this explosion are water vapor and a lot of heat. Hydrogen is a very important commercial element. It combines with numerous other elements to form chemical compounds that we use every day, such as water, table sugar, ammonia, and hydrogen peroxide. Liquid hydrogen is often combined with liquid oxygen to make rocket fuel. America's first mass-produced automobiles rolled off assembly lines in the early 1900s. Today's cars are much more efficient, more powerful, and more advanced. But most still use the same fuel as the cars of 100 years ago: gasoline. When car engines burn gasoline, they release carbon monoxide, nitrogen oxides, and other harmful chemicals into the air. These gases cause smog and acid rain, and many scientists believe they may also contribute to global warming. Gasoline is made from non-renewable fossil fuels such as petroleum, coal, and natural gas that take millions of years to form deep inside the earth. Once the current supplies of these fuels are used up, they are gone for good. Scientists the world over are working on finding alternative fuel sources for the cars of the future. Modern hybrid technology, which uses a combination of gasoline and electricity to power a car, is becoming popular. Hybrid cars are much more efficient than those using conventional engines, but they still rely on the same limited resources as gasoline-powered cars. So some engineers are working on ways to make cars run not on gasoline or hybrid electricity, but on the limitless resource of hydrogen. Hydrogen is the most abundant element in the universe. It makes up more than 90% of all the matter in existence. It is colorless, odorless, tasteless, non-toxic, and highly combustible. Hydrogen has been used to power rocket engines and make devastating bombs. But it is not the combustible nature of hydrogen that makes it a good possible fuel for the future. Instead, it is a basic chemical reaction that scientists have understood for over 150 years. The elements hydrogen and oxygen have a natural attraction to each other. Together, they form water, and when they combine, their chemical reaction releases electricity. This is the principle behind the hydrogen fuel cell. Originally developed for the Gemini space program in the 1960s, fuel cells combine hydrogen, the green atoms, and oxygen, the blue, to produce electricity. Inside the fuel cell, a platinum catalyst splits atoms of hydrogen into positively charged protons and negatively charged electrons. The protons pass through a membrane to bond with oxygen on the other side. The electrons are blocked by the membrane and must flow around it through an electric circuit to recombine with the hydrogen and oxygen and form water. When an electric motor is plugged into this circuit, the electron current is enough to power a car. The only waste product of the process is water. Hydrogen fuel cells have no mechanical parts, such as a transmission, do not operate at high temperatures, and do not need lubricating oils. So maintaining fuel cells should be easier and cheaper than traditional engines. Practical fuel cell cars are still a long way off. Today, it is about 20% more expensive to make hydrogen than a comparable amount of gasoline. And scientists must develop better ways to store hydrogen. Fuel cells are much larger and more expensive than traditional gasoline engines. And current gas stations do not deliver hydrogen to drivers. So most hydrogen-powered cars on the road today are prototypes or test vehicles. But improvements in the technology could one day solve these problems and provide a reliable, efficient, and clean-burning fuel source for centuries to come.
Element number 6 on the periodic table is carbon. The atomic symbol for carbon is C. The appearance of carbon varies based on its crystal structure. As graphite, carbon is a soft black material. But as a diamond, carbon is a translucent crystal and the hardest substance known. This rotation shows a polished sample of native graphite. The name carbon is derived from the French charbon, meaning charcoal, which is a source of carbon. Carbon is classified as a non-metal. It lies in the periodic table's second row, period 2. Each atom of carbon consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of carbon, its nucleus has 6 positively charged protons, plus 6 uncharged neutrons. Carbon has 6 negatively charged electrons to balance its 6 protons. These electrons are found in 2 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, helium. Helium has 2 electrons distributed in a single orbital shell. Carbon has 4 more electrons than helium. The first 2 electrons are found in the sphere-shaped 2s orbital shell. The remaining 2 electrons are distributed between 2 of the 3 lobe-shaped 2p orbitals. Carbon has 4 valence electrons in the second level shell, which determines how it reacts with other elements. Carbon is an essential component of all living things. In the case of this prairie grass, carbon is made available to the plant through the process of photosynthesis. Carbon burns easily in air, so when the grass is lit with a torch, it quickly produces a large quantity of carbon dioxide. Prairie burning is a common practice that ultimately contributes to the health of the environment. Controlled burning of land can be an effective way to maintain an ecological balance. And the release of carbon dioxide makes carbon available to other living things. Carbon occurs in several different allotropes or forms. Amorphous carbon is used to make inks and paints. Carbon in graphite form is ideal for use as an industrial lubricant due to its crystalline structure. Graphite is also used in the production of steel, and it is well known as the black material used in pencils. Naturally occurring diamonds are commonly used in jewelry, but most artificial diamonds are used for diamond-tipped saw blades and other industrial equipment requiring strength and durability. Recently discovered large carbon molecules, known as Buckminster fullerenes, are currently the subject of much scientific research. The carbon in these molecules is arranged like a soccer ball. Carbon-14, a radioactive isotope of carbon, is used to determine the age of ancient objects through a process known as radiocarbon dating. Carbon even has its own branch of chemistry. Organic chemistry is the study of carbon compounds, which are the basis of living things.
Element number 7 on the periodic table is nitrogen. The atomic symbol for nitrogen is N. Making up 78% of the air we breathe, nitrogen is both odorless and colorless. The name nitrogen results as a combination of two Greek words, nitron and genus, which together mean forming saltpeter. Nitrogen is classified as a non-metal. It lies in the periodic table's second row, period 2. Each atom of nitrogen consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of nitrogen, its nucleus has 7 positively charged protons, plus 7 uncharged neutrons. Nitrogen has 7 negatively charged electrons to balance its 7 protons. These electrons are found in 2 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, helium. Helium has 2 electrons distributed in a single orbital shell. Nitrogen has 5 more electrons than helium. The first 2 electrons are found in the sphere-shaped 2s orbital shell. The remaining 3 electrons are distributed among the 3 lobe-shaped 2p orbitals. Nitrogen has 5 valence electrons in this second-level shell, which determines how it reacts with other elements. To get nitrogen in liquid form, it must be cooled to at least -200 degrees Celsius. This makes liquid nitrogen a dangerous substance that must be handled with care. Here, liquid nitrogen is poured into a dewar flask. Because room temperature is much higher than the boiling point of the liquid, the nitrogen instantly vaporizes on contact with the flask. When a flour is lowered into the flask, liquid vaporizes on contact. This creates the bubbling effect seen here. When the nitrogen stops bubbling, the flour and liquid nitrogen have reached thermal equilibrium, which means that they are at the same temperature. The freezing effect of the nitrogen has altered the physical properties of the flour, which shatters like glass when it's dropped on the table. A rubber ball placed into the nitrogen undergoes the same process. Once it reaches thermal equilibrium, the ball is rolled on the table. Once bouncy, the rubber ball has turned into a hard sphere. Hit with a hammer, and it shatters into brittle pieces. The largest industrial use of nitrogen is the production of ammonia, which goes into bleach, fertilizers, and explosives. Nitrogen gas is mostly inert, and for this reason the pure gas is used in place of air when welding to prevent explosions, and for storing sensitive documents, food, and chemicals to prevent oxidation. Liquid nitrogen is an inexpensive cryogenic liquid used for refrigeration, preservation of biological samples, and for low-temperature scientific experimentation. Nitrogen is also a major element in organic compounds, especially most proteins.
Element number 8 on the periodic table is oxygen. The atomic symbol for oxygen is O. Oxygen is a colorless, odorless, tasteless gas that is non-flammable. Oxygen gets its name from the Greek words oxys and genomai, meaning to bring forth acid, because it was once incorrectly believed that oxygen was needed to form all acids. Oxygen is classified as a non-metal. It lies in the periodic table's second row, period 2. Each oxygen atom consists of a cloud of electrons surrounding a compact nucleus that contains almost all of the atom's mass. In the most common form of oxygen, its nucleus has 8 positively charged protons, plus 8 uncharged neutrons. Oxygen has 8 negatively charged electrons to balance its 8 protons. These electrons are found in orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, helium. Helium has 2 electrons distributed among one orbital shell. Oxygen has 6 more electrons than helium. The first 2 electrons are found in the sphere-shaped 2s orbital shell. The final 4 electrons are distributed among 3 lobe-shaped 2p orbitals. Oxygen is a highly reactive element, and the 6 valence electrons in its second-level shell influence how it interacts with other elements. In this experiment, a stream of pure oxygen is directed at a piece of burning charcoal, which immediately begins to spark. The abundant amount of oxygen helps support the combustion of the charcoal, but the oxygen itself does not actually burn. The sparks are small pieces of the glowing charcoal that break away. This reaction is commonly used in steel mills to heat molten iron and produce steel. Oxygen and its compounds are used in water purification, cement and steel making, and welding. Liquid oxygen can be combined with liquid hydrogen to make rocket fuel, and it is necessary for combustion. Oxygen is also required by most living things to breathe. Air pollution is a universal problem that affects the health of all Earth's inhabitants. It destroys the planet's protective ozone layer, and it contributes to many types of respiratory problems, and it has been linked to cancer and other serious diseases. In recent decades, people have become more aware of the dangers of air pollution, and they have made strides to make our air cleaner. But billions of years ago, the Earth's pollution problem was far different from the problems we face today. In our planet's early years, about 3.5 billion years ago, the atmosphere was made of carbon dioxide and methane gases. The first organisms to appear were various forms of bacteria. One group known as cyanobacteria still exists today and are photosynthetic, meaning they extract energy from sunlight. A main byproduct of photosynthesis is oxygen. The oxygen introduced into the atmosphere about 2.5 billion years ago was a serious problem for much of the life on the planet. It was lethal to many of the bacteria that existed at the time. Soon, the Earth's atmosphere was polluted with a deadly poison, oxygen. As some bacteria species died out, others adapted. These organisms began building up defenses to the oxygen-rich atmosphere and found that the element could be utilized to produce energy more efficiently. Over the next few million years, some bacteria evolved into more advanced single-cell organisms. These organisms contained about 1,000 times more DNA than any bacteria. And as organisms adapted to Earth's atmosphere, they gave rise to ever more complex, multicellular organisms. Eventually, the once deadly oxygen became a necessity for nearly every living creature on the planet. Earth's earliest organisms had adapted and helped turn oxygen pollution into a new opportunity for growth and life.
Element number 15 on the periodic table is phosphorus. The atomic symbol for phosphorus is P. There are several allotropes of phosphorus that are distinguished by their color. Shown here is rare black allotrope, the least reactive form of phosphorus. A combination of the Greek words phos and phoros, meaning bearer of light, give phosphorus its name. Phosphorus is classified as a nonmetal. It lies in the periodic table's third row, period 3. Each atom of phosphorus consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of phosphorus, its nucleus has 15 positively charged protons, plus 16 uncharged neutrons. Phosphorus has 15 negatively charged electrons to balance its 15 protons. These electrons are found in 3 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, neon. Neon has 8 electrons distributed in 2 orbital shells. Phosphorus has 5 more electrons than neon. The first 2 electrons are found in the sphere-shaped 3s orbital shell. The remaining 3 electrons are distributed among the 3 lobe-shaped 3p orbitals. Phosphorus has 5 valence electrons in this third-level shell, which determines how it reacts with other elements. Liquid oxygen poured into a flask immediately boils, forcing air out of the flask and producing an oxygen-rich environment. The oxygen is contained within the flask by a bung, or stopper, which also supports a long wire cradling a crucible. Yellow phosphorus is taken out of a jar of water using tweezers, and a copper wire is heated over a Bunsen burner. The phosphorus is placed into the crucible and lowered into the flask. The hot copper wire then touches it to initiate its reaction with the oxygen. The phosphorus immediately ignites inside the flask, burning with a brilliant flame. As the reaction dies down, we see a dense white vapor composed of phosphorus pentoxide, a result of the reaction between the phosphorus and the oxygen. An emulsion of solid phosphorus pentoxide remains around the crucible. Phosphorus has 3 main allotropes, designated by color. A mixture of white phosphorus and petroleum jelly can be used to make napalm, a deadly inflammatory agent that was used during the Vietnam War. Red phosphorus is not poisonous, and it goes into safety matches, fireworks, and pesticides. Phosphoric acid is used in some soft drinks as a flavor additive. Other phosphorus compounds glow in the dark and are used in fluorescent light bulbs and television sets. Element number 16 on the periodic table is sulfur. The atomic symbol for sulfur is S. Sulfur is a yellow powder that has a pungent odor when it is heated. The name sulfur is from the Latin name for the element, which was known to the ancients and was once referred to as brimstone. Sulfur is classified as a nonmetal. It lies in the periodic table's third row, period 3. Each sulfur atom consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of sulfur, its nucleus has 16 positively charged protons, plus 16 uncharged neutrons. Sulfur has 16 negatively charged electrons to balance its 16 protons. These electrons are found in 3 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, neon. Neon has 10 electrons distributed among 2 orbital shells. Sulfur has 6 more electrons than neon. The first 2 electrons are found in the sphere-shaped 3s orbital shell. The remaining 4 electrons are distributed among 3 lobe-shaped 3p orbitals. It is these 6 valence electrons that determine how sulfur interacts with other elements. Sulfur exists in a number of different forms called allotropes. Here, the most common allotrope of sulfur at room temperature, yellow sulfur, is heated in a test tube using a propane torch. The sulfur first melts at 115 degrees Celsius and changes into a mobile orange liquid. Then, as the temperature rises above 175 degrees Celsius, a clear transformation takes place as the liquid thickens and darkens, becoming black and extremely viscous, almost like molasses. This is a physical change as sulfur atoms rearrange themselves to form long chains in a process known as polymerization. When the viscous molten sulfur is poured into water, it solidifies into a flexible, tangled mass known as plastic sulfur. Over the next few days, this plastic form will gradually revert back to its original hard yellow sulfur. Sulfur is used to vulcanize rubber, produce pesticides, and manufacture gunpowder and fireworks. It is also used to make sulfuric acid, which goes into fertilizer and lead-acid batteries. In the Middle Ages, the practice of alchemy was widespread. Alchemy was a chemical philosophy with 3 goals: to turn base metals into gold, a process called transmutation, to find the universal cure for all diseases, and to prolong life indefinitely. Monks in Europe searched for a philosopher's stone that would allow them to turn lead into gold. In China, emperors spared no expense in the search for the elixir of life. While most medieval alchemy proved fruitless, some alchemists did stumble onto unexpected and sometimes valuable discoveries. One occurred in China during the Tang dynasty in the 9th century. An alchemist searching for the secret to eternal life created a mixture that included sulfur, charcoal, and potassium nitrate, also known as saltpeter. While this new mixture did nothing to extend life, it did explode when lit with a flame. The Chinese alchemist had created gunpowder. The explosion of gunpowder is a simple reaction. Charcoal works as fuel, and sulfur is a stabilizer. The main ingredient is potassium nitrate, which provides extra oxygen, allowing the mixture to explode instead of simply burning. The Chinese attached bamboo tubes loaded with gunpowder to arrows to make rocket-propelled missiles. Now one soldier could do as much damage as a regiment. When gunpowder arrived in the West, Europeans immediately wanted to put it to work. They turned to bell makers to engineer an object that was strong enough to hold together when the black powder exploded inside. The cannon was born. Cannons were able to destroy defensive walls that had stood for centuries. Today, we live in a world changed by the advent of gunpowder. The ironic result of the search for everlasting life. Element number 34 on the periodic table is selenium. The atomic symbol for selenium is Se. Selenium occurs in several forms, including an amorphous red powder and the metallic gray crystal seen here. The name selenium comes from the Greek selene, meaning the moon. Selenium is classified as a nonmetal. It lies in the periodic table's 4th row, period 4. Each atom of selenium consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of selenium, its nucleus has 34 positively charged protons, plus 46 uncharged neutrons. Selenium has 34 negatively charged electrons to balance its 34 protons. These electrons are found in 4 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, argon. Argon has 18 electrons distributed in 3 orbital shells. Selenium has 16 more electrons than argon. The first 2 electrons are found in the spherical 4s orbital. The next 10 electrons fill the 5 clover-shaped 3d orbitals. The final 4 electrons are distributed among the 3 lobe-shaped 4p orbitals. Since the electrons in the 3d orbital are at a lower energy than those in the 4s and 4p orbitals, only the 6 valence electrons in this 4th level shell influence how selenium interacts with other elements. In this experiment, you can see an old-fashioned light meter that contains selenium. The gray metal-like form of selenium has the unusual property of increased electrical conductivity when exposed to light. This property makes it particularly useful in light meters. Light hits the white hemisphere, which focuses the light onto an underlying layer of selenium. Increasing the level of light increases the level of electricity conducted. This change is indicated by the needle moving on the scale. Selenium is ideal for use in devices that respond to the intensity of light, such as photoelectric cells, light meters, solar cells, and photocopiers. Selenium is also used to make a ruby red color in glass and enamels. As a trace element, selenium is essential to the human body. It is found in antioxidant enzymes, and the thyroid gland relies on it to function properly.